Sweet. All right, here we go, people. Turn your brains on, turn your phones over, put them somewhere else. All right, let's do it. So people at home, people in here, I'm going to show you in this next 20 minutes the biggest idea of what acids and bases are. And you're going to learn what the pH scale is and what all these things mean in a way that I promise you you never have. Okay? You have heard of acids and bases, right? And you've studied acids and bases in 8th grade science, and probably before that in 4th grade in elementary school, at least talked about what an acid and a base was. And I bet that most of you have heard of the pH scale. If I really quizzed you on it, you'd probably be able to come up with, say, the pH scale goes from 0 to 14, and what number is neutral? 7, that's right. Okay, so you already know what this is, but you don't know anything about it. But using what you've learned in the last several months, I'm going to explain pH to you, and you're literally going to be like, that makes sense, and I understand it. All right, here we go. Ready? Okay. If we have like a liter of water here, right? And we have something like some salt. How am I looking on that camera, Sam? I'm in the screen? All right. We have something like some salt, and we drop it into water. What will happen to the salt? Yes, you can't tell at home, but everyone here screamed that it would dissolve. It will dissolve, that's right. Now, let's talk about what dissolving is, because we've looked at that before. Water is a polar molecule, right? The oxygen in is negative and the hydrogen in is positive. And water is very strong, right? Okay, negative and positive. So the water will literally tear apart the sodium and the chlorine. When the sodium chlorine gets wet, the positive sodium ion will stick to the negative oxygen, and the negative chlorine will stick to the positive hydrogen. And now this salt is invisible to you, right? Right? That's what the solution process is. That's what it means to dissolve. You have these two sodium chloride ions. Boop, and they're torn apart in the water. That's dissolved. Okay? Now, here's what's crazy. You think when you look at water that nothing's going on. And this is almost perfectly what I'm talking about. Here's a liter of water, and this water's been sitting here all weekend. So here's a liter of water at room temperature. So this is this little purple thing that I've drawn here, right? Okay. When we look at this water, it looks like nothing's happening. But that's not true. In reality, if we're talking about room temperature water, we'll call this a liter of water. We'll just say this is 1 liter of water at 23 degrees Celsius at room temperature. So, in this water, some crazy stuff is happening. The water is literally tearing itself apart. Water molecules are very, very strong. They're very polar, and this is something that gives water its unique properties, okay? Now, in this water, the water is literally tearing itself apart. Kind of like those animals that like eat their own young or something like that. Does that make sense? Water is like cannibalistic. It doesn't just dissolve salts and things that you drop in the water. It also dissolves itself, all right? Now let's take a look right here at a water molecule. And let's imagine this water molecule being dissolved. First, we're going to say H2O, that's water. But another way to write this, and I told you about this the first week of school, is HOH. All right? Isn't this the same thing, H2A and HOH? Now, let's just think about water like this, because this is how we're going to think about it for acids and bases. What would happen if you tore this apart? If you tore this in half? Are you going to split this oxygen? No, that would be nuclear energy. That would be nuclear fission, right? So what would happen if you tore this water molecule apart? Well, you would get a hydronium atom, positive, and then you'd have an OH that was negative. That's what happens when you tear water apart. Does that make sense? Now that should look familiar to you. What's that? It's a polyatomic ion called hydroxide, right? So water, sometimes we call it hydrogen hydroxide. If this water molecule is torn apart, check this out. The positive H would stick to the oxygen end of another water molecule, and the negative OH would end up sticking to the positive end of the water molecule. Does that make sense? Does that make sense? Just like the sodium and the chlorine were ripped apart, the water itself can be ripped apart into a positive and negative ion. Now the thing is, that's not really happening all that much. There's a very, very small amount of this happening. And the other thing about it is since this is a water molecule, every time you have an H, you have to also have an OH. Does that make sense? If you just start out with water and it starts tearing itself apart, every time it tears itself apart, you'll have an H and you'll have an OH at an equal rate. Do you agree with that? That's really what neutral water means, is there's an H for every OH. So wait, there's more. Anytime you're looking in a liter of water at 23 degrees Celsius at room temperature, and you ask yourself, well, Mr. Perkins, how many free H's are in there? And Mr. Perkins, how many free OH's are in this water right now? I could tell you not that many. I could tell you the molarity is very, very low. The molarity of hydronium and the molarity of hydroxide is super, super low in this water. How low is it? Good question. This is the molarity in a neutral liter of water at room temperature for H+. 0.0000001 molar H+. And sometimes you'll just see it written as H3O. Does that make sense? If you had an H+ stuck to an H2O, wouldn't it be H3O? I'm always just going to write an H+, okay? And since we have this water molecule, and for every H there's an OH, then the molarity of free hydroxides in a neutral glass of water is always about 0.0000001 molar hydroxide. Now that's crazy. You're like, Mr. Perkins, that's very low. We wouldn't taste that. True. Maybe it's true. As long as you have an equal amount, you won't taste it. Let's write this now in scientific notation, and let's make things start to unravel. 1 times 10 to the negative 7th molar H+. Right? Isn't that the same thing? And how can we write this in scientific notation? 1 times 10 to the negative 7th molar hydroxide. You have to understand this already, right? 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 Yes. Say yes. I understand this. If you don't, you can take your calculator and hit 0.0000001 and then hit second psi, or second number 5 on your calculator, and it will say 1 times 10 to the negative 7. Okay? So 1 times 10 to the negative 7 molar. Let's think of one more way. Let's think of one more way to write the molarity of this H plus. And you're going to be like, what? Ready? You ready to be like, what? Remember, there are very few free H's and OH's in this water. There's so few that its molarity is 0.0000001 molar, or 1 times 10 to the negative 7th molar. Another way to write the molarity of free H's in a liter of water at room temperature is this. It has a percent hydronium of 7. That's what pH means. And if you have a pH of 7, guess what you're going to have? A pOH of negative 7. Does this make sense to you? So really, your science teacher in the 8th grade should have taught you, all right, neutral water has a pH of 7. But now I'm going, well, this is what it means, and this is what it means, and this is what that means. That if you drop some water into water, it would tear itself apart at a very low rate, where the molarity of H pluses is this low, and the molarity, therefore, of OH's is that low. Another way to write that is 1 times 10 to the negative 7th molar, or a percent hydrogen equal to 7, and a percent hydroxide equal to 7. Right? Now, are you ready to be triple blown away? Okay? Ready?
Is the pH always like the exponent?
Yes. Yes. We're going to talk about that later. People at home, a student said, is the pH always like that exponent up there? Yes. As long as we have even numbers, as long as this is a number 1 here in the row, yes. And I'm going to teach you that. People at home, people in here, here's the last true chemistry connection you're going to make. Now, there's no way you can understand this from your 8th grade science, right? Because you didn't know what molarity was, right? Okay? Here it is. Ready? For water, I'm going to write the K. What? I'm going to show you the equilibrium constant for water. And you're going to be like, what? Ready? Here's the equilibrium constant for water. Am I on screen here, right here? The equilibrium constant for water, remember we talked about Le Chatelier and the equilibrium constant, right? Is this. Let's look at the equation for water and what happens to water. Let's look at that as a chemical equation. If we have water, it can break down into, ready? H plus and OH negative. Now if we balanced it, that'd be 1, 1, 1, right? And also, OH and H plus immediately smacks itself back together and turns back into H2O immediately. So when we talk about having free H's or OH's, they're always different ones. These guys would immediately stick back together and another set will be torn apart, right? Right? So if we look at this as a reversible reaction, we can write the K for it. K is equal to, and I'm sure you remember this, H plus in brackets to the power of its molarity. What is the molarity of H plus? It's really 1 times 10 to the negative 7, right? And what's the molarity of the OH negatives? 1 times 10 to the negative 7, right? Right? Over The reactants, H2O, I'll put that in brackets to make you feel better, and that's about 1 molar. Okay, well that's 1 molar because we're just talking about a liter of water. So, let's think about what the K would be here. Let's actually assign a number to a K. You've never actually assigned a number. Right? This is on top. This is 1 on the bottom. What's 1 times 10 to the negative 7 times 1 times 10 to the negative 7? What would you do with these exponents, multiplying exponents? You would add them. Thank you. You would add them. So the KEQ for water is this number. The KEQ is the pH scale. Doesn't the pH scale go from 0 to 14? That comes from the equilibrium constant. This whole last chapter that you did with Le Chatelier's principle actually is pH. Now let's look what happens, and I'm almost done. Okay? I'm almost done with this video. Let's look what happens. It's always going to be 1 times 10 to the negative 4th. So what happens if there were more H's in the water? I'm going to take a 0 over. Let's say there's 10 times more H's in the water. Then that would make this 1 times 10 to the negative 6. So if this changed to the negative 6, what would that OH have to change to? The negative 8, because it's always going to be 14. So if you change the pH, you change the POH, and it's always going to be equal to the equilibrium constant of 1 times 10 to the negative 14. So if something has a pH of 8, it's going to have a POH of, if it had a pH of 6, it's going to have a POH of 8. Does that make sense? Last thing. I'm going to erase all this stuff real quick so you don't have to look at it. Some of your minds are blown. Some of you are nodding going, this all makes sense to me. Some of you behind my back right now are looking at each other going, this guy's crazy. I don't know what he's talking about. All right. I can feel it. Here's the last thing I'm going to show you. Ready? If something is an acid, it's got a bunch of H pluses in it. So how would I make this water into an acid? What if I took like some hydrogen chloride powder and I dropped it into the water? The water would dissolve it. What would I get? I'll get a bunch of free H's and a bunch of Cl negatives, right? Everybody with me on that? That's an acid. Because if I drop that in the water, it gives me a bunch of free H's. And then the pH changes. Does that make sense? Can you think of something I could drop in the water that would maybe make the water a base? If this is the acid, then this is the base. What if I drop some sodium hydroxide in the water? Wouldn't that give me a bunch of free OH negatives floating around? Then that would be making the water basic. Does that make sense? So if you have neutral water, you can pour specific chemicals in it and make it an acid or a base. Right? All right. That right there, that whole spiel I just went through, is the gist of acids and bases. Now I'm going to back up. I'm going to teach you one little bit at a time. But I wanted to get through the whole idea of what acids and bases were before I did that, okay? And honestly, like, you should understand, you honestly should understand what I just went through. You really should, okay? You might be like, well, I understand and I'm going to need to practice. Yeah, that's what we do in school. But at no point during that lecture did I introduce anything new that you've never seen. I just strung a bunch of the Christmas lights together and wrapped it around the tree. Right? Then